Good morning, good afternoon, or good evening. All right, here we go. We're going to look at example 3 or problem 3 from chapter 12, day 2. You should have done chapter 12, day 2, hard for me to say, problem 2 on your own, very similar to the previous examples. But we're going to do number 3, number 4, number 5 all together because they kind of all discuss the big focus of chapter 12.2. Okay, and that is transforming a curved relationship into a linear relationship. Okay, so here we have a situation. You can read all this information about the rockfish and everything, but really what I care about is if we look at this scatter plot. The scatter plot shows a clear curved relationship. Okay, and this curved relationship would mean that we can't do a linear regression analysis. However, we are going to have methods that we can transform those curved relationships into something that's linear, right? And so it looks like you might look at this and say, hey, there might be a power relationship that sets up so that we have a cubic polynomial, maybe, right? A cubic polynomial, a polynomial relationship between the weight and the length of these fish. Okay, you can talk about why it's useful to judge the weight of a fish using its length, because, you know, kind of hard to weigh a fish that is alive at times. Okay, and if you're going to catch and release, right, you want to do as little damage to the fish as possible. So here we have this weight that's curved, but if we think that, hey, maybe a cubic polynomial would fit this well, right? Well, we can look at a relationship between the length cubed and the weight, and we see that that scatter plot is pretty close to linear. Or maybe we do the cubed root of the weight to the length, and that scatter plot is fairly linear, okay? And so we can come over here and we can say, hey, yes, this information does transform into a linear scatter plot. And so we can look at this and say, well, what would be our equations, right, for the two different transformations we did, right? One transformation where we cubed the length and plotted it to the weight, and the other transformation where we left the length alone and plotted it to the cubed root of the weight. Okay, well, my first equation using this over here, we have 4.066 plus 0.0147x, right? We'll call that y hat 1 and x sub 1, right? Well, y hat 1 is going to be the predicted weight, and x1 is going to be the length cubed, right? That's what we plotted. Right, for transformation 2, so y hat 2, negative 0.022, 0.246, or 0.247x, subscript 2, so y hat 2 is going to be the predicted cubed root of the weight, right? Let the computer output really help you out there. And x sub 2 is going to be the length. There we are, okay? Now, ultimately, these are not too hard to come up with as long as you make sure you say predicted, as long as you make sure you have your hats, have the subscripts if you're using multiple equations in the same question, define your variables, and the definition of the variables is simply what they're telling you it is, right? You look at your scatter plot, hey, length cubed is x, okay, weight is y, okay, well, now it's just going to be the predicted weight and length cubed. Okay. Now, suppose a contestant, right, lands a 36 centimeter long fish. Okay. Well, y hat 1, its input is the length cubed. So I'm going to input 36 cubed, right? Put it into my equation with 36 cubed because that's my input, and I get 689.9 grams. Okay. If I use model 2, right, the input there is simply length. So I put in my 36, that gives me 8.87. However, that's the cubed root of the weight, so I have to cube it, and that gives me 697.9 grams, right? So fairly close to each other, not too far off. And we'd say, which one would you choose? Well, it's going to vary by reasons, right? Here, R squared is 99.8%. Here, R squared is 99.5%. So a very, very good R squares in both cases, right? You might say, but the standard deviation of the residuals is more here than it is there. Well, on this one, we went with the cubed root of the weight. So the y values are much, much smaller than the y values over here. So of course there's going to be less variability in the differences between the y values and the predicted y values, right? I'm looking at, hey, what are the differences compared to this? Is the differences compared to that, right? It's a big difference. And so you can really choose whichever one. You might think it's easier to put in 36 cubed at the beginning and not do anything at the end. You might think it's easier to put in 36 at the beginning and then remember to cube at the end. Either way, kind of a personal preference when the things are that close to each other. But when you're asked, you must give a reason and you must be specific on that reason. Okay? So that's one transformation where we have kind of a polynomial relationship. Right? Now, someone else might look at that scatter plot and say, hey, you know what? Yes, it could be a right length cubed, right? But let's think about this as a power model, right? That we have something raised to a power, right? And the approaches there, we're not going to worry about the math too much here, other than we can do a different approach and look at the log of the length compared to the log of the weight. And notice how nicely linear that is for us, right? And notice the R square value, a very, very nice R square value there as well, 99.9%, right? And based on the output, why would it be reasonable to use a power model? Well, if your power model relates your X and Y variables, then the log X and log Y scatter plot, so log Y versus log X, should have a linear relationship. Well, our scatter plot of the log of the weight to the log of the length, right? Once again, remember, it is y to x, right? That scatter plot is linear. And because that scatter plot is linear, then we're going to have a power model. Okay, so let's look at this. If that's my equation of the regression line, what would I have? Well, here's negative 1.89, here's 3.044, right? I can write that down all day long, but I must define. Well, what is y hat? Well, what was y hat? It was log weight. Log weight predicted. Don't forget the predicted, all right? Looking at you, don't forget the predicted. Okay, and then what about x? Well, x is log length. So there it is, log length, right? I want to then estimate that. So y hat will put my input. What is that input? Log of the length. So my input, log of 36. And that's going to be 2.846 if I put that into my calculator. Those that are a little less familiar with using your calculator, right, literally I'm just going to say negative 1.8994. right, plus 3.0494 log 36. That's it. Okay, but remember, that's the log of the weight, so I need to take 10 and raise it to that power to get my answer, right? That if I take 10 and raise it to that, that's going to be my weight, 702.1 grams, which is pretty close to the other value that I got, right? The other ones that we got on the previous problem, right? 689.9, 697.9, fairly close. Okay. Now, of the three regression analyses, right, which seems to be the best for the tournament to predict the weight? Okay. Well, your answers will vary, and one might be better than another in terms of the ease of use. But generally speaking, R square is our simple approach, and the R squared for that power model is greatest and has the least variability in the residuals, right? So we would say that this power model, the one that gave us 702.1, is going to be the best, right? Additionally, notice that for these bigger fish, it's given us a bigger weight. You want to have good reports on fishing, make sure that you have higher weights. So different reasons, but really R square should be your preferred piece, okay? Yes, we can. Now, our next part, number 5, continues with this idea on transformations. And quite literally, if you just rewatch this video, if you don't quite understand at the start, or read it in your textbook and say, hey, what do I have? It really is just about how can I transform things, Okay, so here we have, once again, hey, here's this curved relationship, but now we're looking at a different relationship. And this talks about Moore's law, and you can read about Gordon Moore and Intel Corporation and computer chips and all of that sort of thing. And Moore's law, right, if we look at this curved relationship, we might say, hey, you know what? An exponential model might be better than a power model. A power model grows fast, but an exponential model grows much, much faster, right? That's very important to note about the exponential models growing much faster than power models. So if we look at this, we say, hey, here's the scatter plot. Why would an exponential model be good? Well, look at our scatter plot of x versus the natural log of y. Right, here's x, here's the natural log of y, and that scatter plot is pretty close to linear, especially if I don't look at the very end, right? For the first 30 plus years, that's very, very close to linear. It does seem to double every 18 months, right, as Moore said, right? But it does kind of start to taper off there at the end. We start to flatten that curve. But here, yes, fairly linear. And so if I have an exponential relationship, then that x to the natural log, that x natural log of y scatter plot should be linear. And we notice that the natural log of transistors versus the years scatter plot is roughly linear. So give the equation of the least squares regression line, define any variables you use. Well, y hat, right, there's the 7.047, 0.3658, right? We've got those values. And once again, we have to make sure that we define y hat, the predicted natural log of the transistors. X, the years since 1970, right? Don't make it hard on yourself. Literally just read the graph, right? Here's a scatter plot here, there's a scatter plot there. Write it down just like you see it. Then use your model to predict the number of transistors on an Intel computer chip in 2020, right? Well, 2020 is 50 years after 1970. So I would put 50 into my model, right? If I put 50 into this model, I'm going to get 25.355. However, that's the natural log of the transistors. So I need to take it on, exponentiate that on a base of e. So e to the 25.355. And if you don't realize that that's a big number, here's how I could write it with scientific notation. And if you don't realize that's a big number, that's almost a trillion. 10 to the 12th power would be a trillion. So what does that tell us? This is more than 100 billion B transistors. That's a whole lot. That's amazing what technology can do. Okay, then let's look at the residual plot and discuss the appropriateness of the model. So if we look at the residual plot, right, and we kind of look at the first few years, hey, things are up, down, right, kind of, right, not too far apart, but a little pattern. But now we start to see a bit more of a pattern here later on, right? As we get past 30 years, we do seem to have a little bit more of a pattern, and we notice that, hey, after 30 years towards 40 years, this linear relationship doesn't seem to be linear as much anymore. Okay. However, relative to logarithms, these are very, very small residuals. And so what we might say is the residual plot does have a distinctive pattern after some number of years, about 25. So you need to be careful, right? The transform plot is certainly linear, but it is leveling off after about 40 years, right? So while we might use the model or might have used the model in the past, maybe now it's time for a new model. You just want to be careful about those things, right? A model works until it doesn't. And that's an important thing to realize, okay? For those of you wondering, that's some of my familia from Mexico, right? That was at a little family get-together, or actually, I think that was a wedding this past winter down in Guadalajara, and we got, you know, the family, the cousins, and if you look in there, yeah, that's mostly all cousins and a couple of aunts and uncles. All right, so y'all have a good one. Stay safe, and make sure that you Zoom or that you email if you have any questions. All right, So here's my tia Patti, there's my tio Pato, my cousin Chucho, Mr. Worldwide, my cousin Marcelo, Mr. Hitarachi. He'll probably be the next one getting married. He's a fiance of one of my younger cousins. So have a good one. Adios.